Alright, so on to the solution. Okay, so what I thought about comparing and storing it elsewhere, storing the result elsewhere, was actually the solution, but the actual solution was a little different. So we'll just create a list node, empty list node, right? And then what I can do is while list one and list two, we'll go through each of the lists. See if um, let's say list one dot val is less than list2 dot val. If it is less, let's say less than equal, okay, will so we will what we'll do is store the uh, show the reference to the list one, right? Then increment list one to the next element. Hmm. Okay, so list one equals list one dot next, right? And then I want to append temp. Else, what we want to do is then in the end we'll check d dot next equals list one if list one, right, else list two. Hold up, we want to check, we want to give it list one if list one is else list two if list two list two. Okay, then we return d dot next. Okay, yeah. I see the problem here. And d. Let's see. Okay, 0 and 4. That's right. Current equals d. We hold the, then we go cur dot next equals temp and cur dot next and cur dot next, and then let's try this. Okay, still 0 and 4. Okay, val 0 and then none. Val 0, list node 0. Okay, so while list 1 and list 2, we want to detach that list, right? Current dot next equals temp. Okay, hold up. If I go, I store the reference next here, and then I increment right. Let's try this. Okay, so we have one. I have one, two, three, four, right. So 0 and then 0. Okay, correct. Okay, so we take the value, we increment it, so we list one is no longer there. Then if list one is, let's see, if list one is not empty, then we assign list one as list 2, because one of these lists have to be empty, right? Okay, start with empty list, current iterator in the empty list, and then we just append to the list. Okay, then when the loop ends, one or both the lists are empty. If one of them is not empty, then we will append it to the new list. Okay. Okay, since the new list contains an extra node at the beginning, we will simply return the next node. Next, and that is it, right? Okay, then we submit it. Alright. So let's save the solution. Alright. The solution from algom.io. Let's, okay, so this is done. Then linked list cycles. Okay, linked list cycle is given head of a list. Given the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in the linked list if there is some node in the list that can be reached again by continuously following next pointer. Internally, position is used to denote the index of the node at the tails. Okay, internally, position is used to denote the index of the node that tails next pointer is connected to. Note that is not passed as a parameter. Okay. Return true return true if there is a cycle in the linked list, otherwise. Okay, so we have 3 2 minus 4. The position is 1 from where it starts. Okay, be true. Okay, there is a linked list. There is a okay. There is a linked list. There is a cycle in the linked list where the tail connects to the first node, 0 indexed. Okay. So there is a cycle in the linked list where the tail connects to the first node, 0 indexed. Okay. So right, what can I do is okay. Pose is -1 or valid index in the list. Position is 0. Input. Do you like just run it? Position is 1. Okay. Note that pose is not passed as a parameter. Okay, given the head of the linked list should remain if the linked list has a cycle in it. There is a cycle in the linked list if there is some node in the list that can be reached again by continuously following next pointer. Internally, pose is used to denote the index of the tail's next pointer is connected to. Note that position is not passed as a parameter. Okay, so input, there's a cycle in the linked list. Okay. So position is not a part of this. Okay. So what I can do is have this okay, right. Okay, see if there's a cycle, right? Okay, how about I go, I I break off the list, right? I break off the list. I'll append it to another list, right? I'll break off, then append it, right? Okay, so let me append it to another list now, but then cycle would remain, right? You break off, you connected here is 0 1 2 3, right? So this is 0. Then right, okay, so then I break it off. If I break it off, we get this. And then it would cycle back. Okay, so we can't really break it off. Okay. So maybe save the individual nodes, right? Say save the individual nodes. Okay, so let's say I have this node. I'll push it, right? I have 0. I have broken it off, and now I'm currently pointing here. I say next is none, then I put it here. Then we can correspondingly check if the next exists here, right? We can go if the next is any of the lists here, right? Okay. If it is any of the list node here, right? If no, then we break it off. We break it off. We go to. Then we again check with this next. Is this next in the list? No. So we break it off. We push. Right. We break it. No. Okay. When do we check the next? We go. We have an empty list in the end with the beginning. Right. So we go 2 here. Then we check. Then when I reach 3, I will check if 3 is next anywhere in the list. Yes, that node exists in the list. So we go cycle exists. True. Right. So this should be simple. I'll go while head, right? Go nodes. Okay. So I want to break off the node while head. So current equals head. Okay. Okay. So I can go if nodes, they are nodes, right? And if current dot next in nodes just a linear search. If current dot next in nodes, then we return true. Right, return true. Else, what I will do is I'll go nodes dot append. Okay, maybe I'll take the reference. Then equals head, and then head equals head dot next, and then oh, maybe I can just store the current node. Right, I can store the current node. while head, or I'll say while cur. So I can go with if nodes, right, head, uh, then I want to append the current value. I want to append the temporary value, and I will go current equals current dot next, right? So we'll check if the node is in the list, right? Then we do, then we return true that there is a cycle. Else, we return false. Let's try and run this. What do we get? Seemingly taking a lot of time. Oh, okay, because first time it won't run. Alright. Okay, so if not node, so I'll just append the current value, right? If nodes, else I want to just append the current value. Node dot append temp. Let's try that. First time it runs. Okay, so that is it, right? If I submit it, and the solution is really slow. Okay, so it is really slow. Where's complexity? Should be O of n. Yeah, it is O of n, but 29 of 29 test cases. Okay, but still it is really slow, huh? Okay, what is another way? So this way works. I'll say works, but slow. Okay, then what is another way to detect cycles? Huh. You're literally here. Okay. Let's copy this. This is 141 linked list cycle. Okay. This is my solution. My solution for this is running really slow. I don't know why, but for some reason it is running really slow. Brave, bro. Okay, so let's get rid of some things here. Very log. What is this? Entire websites. This is. Yeah, we don't need that anymore. delete that. Yep. Sprint have okay. Alright, bugs. Go here. Writing emulators. Okay. Tokens, and that's okay.
GP.
Okay. And encapsulation. Okay. It's allocated on the app. This. Thank you, my man. Thank you. I think it should be a little free now. No? Still? Yeah, comparatively it's free. Okay. So, my solution for LeetCode 141. Solution. Linked list. Cycles. Okay. Parent.next and nodes. Okay, this is a O of an operation, right? If uh, if I can turn this into a set, okay, let's try nodes set set dot add, right? So it works like that. Have Python doc set. Okay, set equals what are some of its functions? Yeah, add. Okay, adds an element to a set. Okay, so if nodes, if current dot next dot val in nodes, then temp is current dot val, and then I want to add here current dot val. Next, add temp. Okay, let's try this. So we won't waste any time searching, right? Yeah, okay. Two. This is attribute none type object has no attribute val. Okay. If nodes, if next current dot next dot val in nodes. Okay. I'll go while current dot next. Right. While current dot next. Does that work? Works here. And still okay. Still okay. While current dot next. This is on test case third. Okay, 1 and 2. Was there a cycle? There was a cycle. Okay. Okay, so I think how much time? How to time program block in Python. Okay. Put time, start time, perform counter, time dot, perform counter, elapsed time, end time as start time. Okay, let's write. Okay, so let me make a dictionary, right? A dictionary, okay, and I will store the list nodes with their index, right? With their index slash position, right? So still go with current right. If cur dot next, I just have so I equals 0, right? Okay, so O of 1. So if nodes, if current dot next in nodes, return true. Else we go nodes of current, nodes of current equals I. We go I equals I plus 1. So if current dot next in nodes return true, else nodes current of I equals I, and this is okay. Let's try and run this here. Does it work here? Okay, runtime 50 milliseconds. Okay, 50 milliseconds. Ooh, dude. Let me just get this. Right. Okay. Before set, right? Okay. And what was the runtime like here? 43. Ooh, dude. This is like, okay, if I want to use test case, right? Okay. This is really slow for some reason. Okay. and when I run this, okay, let's try and submit it. Okay, so ooh, nice, nice, nice. My runtime was so bad. Okay, so spending what is even faster, you know, what can be uh, fast, what can be a little fast solution than this. Five. Solution 2. Solution 2 for LeetCode 141. Better runtime performance. Okay. Okay, so it took 49. Okay, how can I okay, I will show the list nodes with the indexes. Okay, how can I visited, right? Basically I would have to make a chart of visited, right? Value 1 visited, this visited, like basically that is it, checking again and again for the same value, right? Like we can mark this visited, this is visited, this is visited, this is visited, then we come back, then we see is this visited. There is extra space, so instead of will that make a difference if I don't store, right? Okay, so okay, let's take a look at the solution.
Hey guys, Greg here. Let's solve linked list cycle, LeetCode number 141. It's claimed. Now we're given head, the head of a linked list as usual, and we want to determine if that linked list has a cycle in it. Now we don't really need to read this, it's pretty visual. So if we are going through the list and then we actually never stop going through the list, well then we have a cycle. So there's really no completion to this because it keeps wrapping around every time we get to the -4. So in other words, it basically happens because we're traversing and then we actually have a next pointer. So this next pointer is actually pointing to a node that we've already seen before. And that's going to give you a clue into our first solution. Okay, so suppose we had this list here, and you can see there's no cycles in it. If we were just to traverse this, we'd point C or cur equal to the head, and we would just kind of go through by setting cur to be cur.next. We could go through while cur is a valid node, and if we got out of bounds or when it equals none, well then we're out of bounds, and so clearly there wasn't a cycle. But say that there actually was a cycle, and so we'll point 4, say, over to 2 here. So now we're in the circumstance where if we were to do this, if we were to send cur through, just setting it to cur.next, well this is actually going to go on infinitely. Okay, so yes, you could return false if we get to the point where cur is none, but otherwise, how do we actually detect this cycle? Because this is an infinite loop. Now, if you ever want to detect duplicates, then you could use something like a set or a hash map, anything that uses hashing, so we'll just use a hash set. So in here, we'll just store node references to the nodes we've seen. And you want references, not values. You don't want these to be integers, because if you were in the case where actually these had 2 different values here, well, this is not an issue here, okay? This part right here does not imply a cycle because these are 2 different nodes. They have the same value, but they are 2 different nodes. So we don't want to put, you know, integers over here. We actually want to put node references. And it's really easy to do that in code. Even C here, you could actually just put C into the set, and that would use the memory address. That would work just fine. For the visualization, it's a little bit harder. So I'm actually going to write the number, which is going to indicate which one of these it is. But know that I'm actually not not putting integers here. I'm actually putting references to the node itself. And you can do that. You can hash on memory addresses because a memory address is immutable, which is the definition for hashing in most cases. Okay, so we just put this node into the set here, and then we will move forward by setting C to bc.next. C is just short for cur. So we see 2, so we're going to put that into the set. We haven't seen any duplicates yet. Here we go over to 3, we will put in 3, and this is going to plug in 4 here. And at this point, we actually traverse over back to here. And so before we put stuff into the set, we're going to ask if it's already in the set. And so it is already in the set. Okay, this node reference here, that is already in the set, and that is when we would return false here. Okay? Okay, and imagine we didn't have some cycle, so we'd actually get out here, and so C would be none at some point, and that's a case where we could actually return true. Okay? Now, the only problem with this solution is that this has O of n space here. Okay? We're using a hash set to store these n values. So the time is O of n. We're not going to be able to do any better than that. There's an algorithm called Floyd's cycle finding algorithm. There's a couple names for this algorithm. It could be called like slow and fast pointers. Could be called, there's this guy named Floyd that came up with it. So Floyd's cycle finding algorithm, tortoise and hare, because, you know, hares are faster than tortoises. Kind of like a slow pointer is, you know, slower than a fast pointer. Let's see how to do this, and it's going to end up being constant space. Okay, so for this example, it's actually not quite necessary, but I find it's useful to start off with a dummy node. So this is just creating a new node. The value of it doesn't really matter. And we're going to set that dummy.next to equal the actual head. Okay, so that way we can set up our 2 pointers. We'll call them S for slow and F for fast. So those are both going to point over to the dummy. And the fast pointer is going to move 2 steps every time the slow pointer moves 1 step. So the fast pointer moves twice as fast as slow. So say that we were to move slow once, immediately after we'd move fast over twice. And then we move over once, we move fast over twice. Well, F can't move twice here. It actually can't even move once. And so we can detect that right here. And since fast can't move anymore, well, that means that we actually found an end to the list. And therefore, there wasn't a cycle, because if there was a cycle, well, then you would have been trapped in that the whole time. And so there must not have been a cycle we were about to escape. And so since it was trying to go out of bounds, this is actually a scenario where we'd return false because there wasn't a cycle. Okay, but again, say that we were in the scenario where there actually was a cycle. So maybe 4 was pointing over to 2. So if we were to do this again, we'll point slow and fast over to the dummy. And then we're going to move slow over once. Fast is going to go over twice. Slow goes over once. Fast goes over twice. Slow goes over once. Fast goes over twice. Look at what happened here. They actually started pointing at the same node. So they are pointing to the same node reference here. Now, what's super crazy, and I feel very counterintuitive, is that if there is a cycle in the linked list, then it's actually guaranteed that if you run this algorithm where we have 2 pointers running at a different pace, at some point, they are actually going to equal the same node. They might not equal necessarily this node, but they're going to equal some node that is, you know, part of that cycle. Okay, so I don't really want to talk about why that's true, but just know that this algorithm actually does work, and there's a theorem behind it. Okay, so let's write our code. We're going to set a dummy node equal to a new list node. We really don't care about its value. We're just going to specify that dummy.next is equal to the head, so that connects them up. Now we're going to set both slow and fast pointing equal to the dummy. So that basically says, you know, fast is going to point to dummy, and slow is going to point to fast, but that means they're pointing to the same thing. While we have fast and we have fast.next. Why? Because we're going to set fast equal to fast.next.next. So this code here is assuming that fast.next actually exists. It has to be a node, because if this wasn't a node, well, something like null or none, that's not going to have a .next. So each time this runs, we're making sure fast is a node, and we're making sure fast.next is a node, so that we can move fast over twice. Okay? And so every time fast moves over once, slow is going to move over once. And if you are ever running into the case where slow is fast, so if their memory addresses are the same, they're pointing to the same node, so that means there must have been a cycle by Floyd's awesome algorithm here. We return true in that case, and then otherwise, if you actually escape this loop, well, that means that this expired, and so at some point, you basically got through the list, and if you got through the list, there must not have been a cycle, so we can just return false there. Now, the time and space here is not super intuitive, because if there is a cycle, we don't really know how long it's going to take fast and slow two equal each other. We know they will equal each other, but it turns out that the time complexity, they are going to find it in, big O of n time. It's not going to take that long for them to find each other. And the space complexity of this algorithm, this actually doesn't take any space. It holds just, a dummy as a new node. That's fine. And 2 pointers, that's really all it is. So that's going to be constant space. That's why it's better than the hash map solution, because the hash map solution, or the hash set solution, that would be big O of n. In this solution.
Okay. So, go. The solution is based on the Floyd algorithm, where we move a fast, slow pointer, instant slow pointer through the list, and at some time it is guaranteed that they will meet. If not, then there is no cycle. Okay, so we start with dummy node, and we go slow is equals to fast is equals to pointing dummy. So while fast and fast dot next, we don't want to reference none. So we go fast equals fast dot next twice as much, and slow equals slow dot next, just one step. So if slow is fast, then simply we can return true, else the loop will break and we can return false. So dummy ooh, it returned false. Alright, so where did I go wrong? Okay, fast equals fast dot next, right? Twice as much. If slow is fast, return true, else return false. Okay, so what did I do wrong here? And it tells me that this is wrong, because dummy, okay, dummy dot next, oh, shit, okay, my bad. So I even have to point to the list as well. Okay, 60, oh, okay, it's somewhat better. Hey, what are these people doing? Import lambda open display random.txt, right? Same. Let's try second one. Same algorithm. But they are okay. While fast is not none and not none. Huh. Next is not none. Okay, so I can also, if I forget this, I can just go, this is head, right? Okay, what is this? No duplicate begin store already visited. Okay, so it goes visited in it. So it is the same. It is the same, right? It is the same code overall. Okay, so this is solution. Leave it. Not go. Dummy is an empty list node. When we go, dummy dot next is head. Okay. So there we go. That is it for today. Let me mark it as completed. This is middle of the list. This is using slow and maybe I can do that. It is also using right. I'll go fast equals slow equals head, while fast fast equals fast dot next and slow equals slow dot next. Okay, if there are two middle, then the return slow. Let's try this. No. Okay. While fast and fast dot next. It is simple. It just works on the yeah. Okay. So this is also done. I knew that. When the fast pointer has reached the end, the slow pointer would have covered half as much distance. There we go. Okay. So linked lists are done. Then I can move on to binary search. Oh, binary search. Yes, I can do binary search, Yeah. Target int. Okay. So I will low equals list of low equals 0 and high low equals 0 and high equals len of nums -1 we go, while low is less than or equals to high. Go middle equals low plus high minus low divided by 2. Then if int otherwise minus 1. Okay. If nums of middle is less than target, so we'll go high equals middle minus 1. Else if nums of middle is greater than target, so it lies in the right half, so plus 1, else we go return it wants the return its index, return middle, return -1, right, return -1. Len, yeah. Okay. We are submitting too frequently. I just want to run. I'm not submitting. Okay. Nums of middle. Okay. Rest indices must be integer. Or slices. Okay. Okay. So this is integer division. Okay. Target 9 should be 4, so it returned -1. Okay, so if the target nums middle, if target is less than the middle, low is 0. Okay. Okay, see, we have middle 0, 1, 2, 3. Okay, nice. Integer division. Okay, maybe I'll just stick to simple low plus high. Divided by 2. Let's see. Okay, still wrong, so there's something wrong in my algorithm. Okay. Okay, if target is less than the middle element. Oh, if target is less, so I have to go switch these. Target is less than nums of middle, right? And if target is greater than nums of middle. Okay. Alright, so this is done. Okay, so I'll say that is it for today. Middle of the list, I think this is right. Middle of the linked list. and reading not. Oh, don't save it. Main.py. Cool. This is my solution for LeetCode 876. Middle of the link list. Okay. Then let's create new binary search. Okay, so this optimization, but this is dynamic, right? Integer division. I'll create an index document. This is my solution for LeetCode. LeetCode 704. And research. Okay. Search insert position. I've done that. Traditional quest condition based. Just bad version. Okay. So that is it for today.